instead of thinking of the domain of physics, what is the domain of physics? How would you say it? What is it responsible or interested in? What's its domain?
What I tend to view it as is cosmology and the most, drilling down and drilling up, like, subatomic particles, molecules. Even I kind of put chemistry into the world of physics,
You might put that word on there.
Okay, I
It's
actually like that.
what is real?
What is real?
Right.
That's what it boils down to.
Okay. Of course, we have a whole bunch of psychological issues about the question itself, because what is real kind of a lot of times comes from what you're projecting, and that's what determines what you're investigating and so on. But
right,
still.
and it also explains why physics has its roots in philosophy, because that question, what is real, is very philosophical.
Yes, I think it's this focus on trying to determine what's real, first of all, it's been dead-ended. Okay? Physics hasn't made any progress in 50 years. It might be taken as a slight, but I think most physicists know what I mean. We haven't made any revolutionary changes to the way we see the world in 50 years. Okay, we've measured the Higgs. We've found out that the neutrinos have to have some positive mass, and what it is. We've discovered a few details in the last 50, but nothing revolutionary that really makes us think some new way. Right? It just makes us more confident that the way we were thinking was right, even though it hasn't given us the full answers. I think trying to discover what is real has left us a little sidetracked because of the goal, the reach you're after. What is real? You don't know ahead of time. So if you already have an impression of what's real, and you're looking for what is real, you're looking for what you already believe.
Right.
Right? You're not looking into the world and getting feedback from the actual world and having to adjust your beliefs. You're just reinforcing your beliefs. So we've gotten kind of trapped because we lost the feedback system. I think there's a better focus.
And actually, in order to ask the question, what is real, you have to be able to let go of all your other answers.
Yeah. I want to know now, what persists? There's a different little focus, but persistence brings us to this fundamental notion of
reality.
time.
Actually, persistence is one level even below reality. There is no reality if there is no persistence.
Mm-hmm.
So persistence is almost like the subatomic particle of reality.
Yeah, and the rules that determine whether or not you persist are what we're establishing.
Yes.
Fundamentally. That's it. So persistence, if you persist, then you have a property. If you
Shit,
persist in any way at all, do something over and over, you have a property.
I can't believe you thought of all this shit. I can't.
I didn't think of it. That's my point. I remembered that to be a scientist, you have to stop trying to believe in what is real or that you have it right? I'm trying to look through my lens of what I already believe of what is real and admit to yourself there's a lot of fundamental gaps in that story, whatever it is, because the story we currently have doesn't explain the mysteries we need to explain. The constants of nature are all fundamental mysteries. Not a single one has ever been attached to a story in physics, right? They're complete blank mysteries right now. And they're identified as what? What are they? The elementary parameters that describe the physical essence of our existence. I don't know how you get more fundamental than that or more important than that. They're literally the most important numbers we've discovered.
And because you can't go any lower.
You can't go any longer. So the process now, instead of trying to worry about define what is real through my lens of real, get back to a process that allows you to investigate and get feedback from the world, not from my belief. Right? Like we did when we were a kid. It was all new, but you were discovering things that were actually there and trying to reinterpret what is this thing? Because you've never seen it before. You got to find out what its function is and how it fits into things. And sometimes it doesn't fit so radically to your world that it makes you update the whole meaning of what the world is. Right? So doing this, switching to a concept of, let's think of a science as a logic tradition that first establishes the rules for persistence. What can persist? And that rules, by the way, you can encode them algebraically or geometrically, and they mean literally the same things. There's two ways to talk about them. You can algebraically talk about geometry. You can geometrically talk about algebra, and they can be references to the same sort of operationally closed systems, right?
But the insight, I don't think you're giving yourself enough credit. The insight to see that reality is made up of building blocks of persistence.
Yes, but
is
I
an
haven't gotten to
amazing
that
leap.
point yet. I want to make sure you don't get confused about where it comes from so that you can own it your own self too, instead of thinking somehow went past you there. The insight didn't come at the point where I realized this. I ended up realizing this eventually by just taking the data set, the constants of nature, looking at them very closely, and first realizing there's only 5 dimensions that all of them, up to 5 dimensions they all run. So it wasn't an insight that happened right away. The process was the thing that happened. I got a process where I could now ask a question and get a feedback answer from nature. What do I mean? Literally, you have the speed of light equals a number, right?
And you're explaining how you figured out that
This is a data point. This is a true relationship between the base dimensions of meters and seconds. Whatever that means. If you just believe meters are something important, it's a fundamental dimension and a fundamental dimension, this relates somehow the relationship between those dimensions, the cutoffs.
I see what you're...
And we have a list of 44 constants that all are defined by a number and an arrangement of dimensions. That's different each time because it's the dimensions that are arranged that you're talking about. This refers to this arrangement.
I get it. So then what ends up happening, then the next clue is meters and seconds. Because that leads someplace...
Or you could do the same thing and list all the constants now and notice,
okay, go wide or go deep, right?
All clues always include the meters that are seconds, meters, the next one is charge or coulombs, and kilograms, and Kelvin. At some point you realize those 5 things, by the way, there's also a mole and a candela, or candle, right? And these are, do you know what they are already?
Mole, like that's a measurement of size, like
a measurement of amount.
Amount, right? Like a little.
But it's a fixed. This one's not a fixed. This one's actually fixed based off the human eye. Okay, this is the only thing that's not fundamental in any of these, but it's going to be a really fun conversation when we get to there. This one's a fixed relationship that's defined
how
by
big how much something holds, right?
1 over the Planck charge and the Planck mass. Together, when the Planck charge and Planck mass are together, it defines an amount referring to the mole. It's a combined unit that gives us an amount.
I didn't know that.
No one knows that. Okay. But okay, whatever that
I just thought it was...
With this relationship, we have a clue. So we know, first of all, it's a really big help to know that these dimensions, the 5 we care about, that they're all part of the coherent set of dimensions, right? So they're intrinsically important, and to remember that we have the boundary conditions for each of the Planck constants. So we have cutoffs for each dimension. Well, then that means, well, we care about the boundary cutoffs of each dimension, and these are relationships between 2 dimensions. Well, it turns out it doesn't take much from that to say, well, this is meters, so Planck length would be its cutoff, right? What is this going to be, Planck time? How close does that get us? It takes us the first 7 significant digits to the right power.
Holy shit.
If you can identify the boundaries in Planck terms, and you know the dimensions in this coherent set of units, then the number you get kicked out is already set.
Oh shit.
All these things are relationships fixed between the boundaries.
Wait, this is like so shocking it doesn't even seem possible.
I know, and it's so shocking if it was just for the speed of light. It's for all 44. Now you can find them all on your own, because all you have to do is know the prescription is this for every constant of nature. Any one you want, so constant. So you would put the measured value and its dimensions. So number, times 10 to the something, but units, it has to have units. So number and units in every one, okay? That's a measurement. That just comes from a measurement, that's only. And that's every time going to be equal to, I can't go over that.
It'll always be one of the 5.
It'll always be equal to some primary action. So I'll do that called A sub P. Some action, geometric, wave ranging things on some primary set of boundaries. It could be 2 or 3 or 4 or 5. It could be divided by each other or squared, it doesn't matter, but some set of boundaries, but they have to be Planck boundaries. Okay?
Wow.
And then there's going to be the opposite side. There's an internal and an external arrangement that balances everything in the system because it's come from it's projected from the inside. So now we're just going to do the inside. And it's going to be 1 plus or minus some action terminal, some terminal action on this side, and I can put boundary terminal, but the boundary terminal is always a fixed thing. Every arrangement you can think of gives a constant of nature, but this one's always fixed. Why? Because the internal arrangement is very, 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 very fixed. And what is it? I'm going to replace it with a different symbol because it's not a variable anymore. It's always just one thing. I'm going to call it this. And that equals the Planck length times by the Planck mass over the Planck charge squared. That's the external constructive arrangement of these boundaries that's keeping the inside-outside circles getting their expressions over and over and over. You could call that the entropy boundary of the whole arrangement. That's where everything goes to be completely torn apart. Okay? So that one is just this is the construction, that's it. So you put in a constant of nature, a number that you got from a measurement. This one, plot the number with the meters per second in here. And now you know it's going to have to be some geometry, some number geometry. By the way, this is always going to be pi, 2 pi, 4 pi, 1 over pi, 1 over 2 pi, 1 over 4 pi, something like that. Or using the je1s or je2s.
But did you start with the number and work your way back to the formula?
Well, it turns out it's also very frequently. So A sub P could just be 1. It's just a unitary relationship. And in this case, we're only comparing two things. And it turns out to be 1 in this case, which makes it a lot easier to discover that its patterns are there, right? So the constant later, we got the speed of light, put in the number for it. And that equals 1 times by the primary boundaries, Planck length, over the Planck time, times by 1 plus or minus, let's put plus in there. And then we have a question here, and we can easily go put it in the computer and solve. Because we know that this value, by the way, the number 1 times 10 to the negative 7.
That's what that equals?
That's what that equals, which is a mind blower to begin with. If you take the value of the Planck length times by the Planck mass, the number you get, string of digits that looks random to you, is the same string of digits that you square the Planck charge.
It's the same set of numbers?
Same string of numbers. Yeah.
How many digits?
14. Everything has
Okay,
14.
so it's all the same.
Yeah.
It doesn't
Yeah.
even seem possible.
Yeah, it means this constructive arrangement is making so we have, remember, outside, inside. How do I know this one's inside? Because it's smaller than that one. How do I know? Because this terminal boundary is whatever association it is. This boundary is times 10 to the negative 7.
So that's way smaller.
Whatever's in here, it's 7 orders of magnitude smaller than whatever's out there. It means I can ignore this if I only care about being right the first 7 significant digits, right?
Okay.
Which makes it a lot easier because I can always solve for these two first and then know I'm right about 7 significant digits, and then put this back in and go solve for this one. It really reduces the work. But importantly, it's important to remember that this constructive arrangement is setting up a fixed 7-digit shift in base 10 into our construction permanently. And so centrally that it's the thing that's in every prescription for every constant of nature. Because it's how the external boundary is arranged.
Wow.
Okay, so that's enough for anyone to just now go look up any constant of nature, make sure that the way you write it down is in the units that are the coherent system of units, right? It'll be listed that way too, but they also list them sometimes in many other ways at the same time. So look for the one that's listed in the coherent system of units because you know that the relationship between those coherent system of units is what we're encoding by the Planck constant and so on. And then the number will be there, the power will be there. You use the power in the constant, the dimensions of the constant, and you just interpret them in terms of the Planck constants. Pick the dimensions and associate with the Planck constant that defines that dimension's boundary.
Okay.
In every case, you put that, and that determines the boundary here. Now you don't know this one, but you do know that one, and you're pretending this doesn't exist yet. Right?
So then you can figure to that.
You can just check. Now lots of times this is 1, so you already, as soon as you do that, you find out you already got the right number right, almost, right? For the first 7 significant digits. And then just check for the next one. And interpret them geometrically. You look for the cleanest geometry, or first of all, you can stick to the rules. It has to be right out to 14 significant digits. It can't be sometimes 12 or sometimes 9. It has to be right out to 14 significant digits for it to be a geometric closed claim that balances what we're saying, right? So because you know it has to be that extremely right, it's not like it's a lot of guessing, right? Sometimes if you don't know what thing to guess, you're not getting around. Maybe you didn't pick the right jeu or anything, and you never get something. But once you put in the right jeu, times pi squared, like, yeah, that's it. Really easy to identify. So it wasn't a genius that I came up with. I came up with a way to ask. I came up with a way to take a number that nobody understands and put it in here, and it spits out the solution. And the solution is a geometric thing that then made sense, or at least to geometers. I might have to go look up, oh, what is, I've never heard of the Dottie constant or the Lemniscate constant, what's that? I might have not known what they were, but Wolfram Alpha knew what it was, and when it comes up with, it could be these 4,000 things put together, that gets you close, or these weird things put together get you close, or 2 pi. Right? It's not, when it's like that, it's not so hard to know. Yeah, I'm gonna go with the 2 pi. Yeah, so we have a prescription, and a prescription gives us a feedback. Right? It gives you a way to look into the world a new way and get a touch back from the world. It says, here's your answer, Lemniscate constant. I don't even know what that is. Okay, Google, Lemniscate constant. Oh, it's related to the gamma function intrinsically. It's related to all this double periodic systems. Oh, this is interesting, right? This great way to follow the trail. So it wasn't that genius insight came up with the answer. I didn't come up with this answer at all. I was driven to this answer from asking 1,000 questions.
I can see how this would eventually lead to that.
Yep.
At some point,
it took a
there
while.
must be a minimum unit or minimum persistence.
Well, the thing that slowed me down forever was this.
We wouldn't have a universe.
When I was doing this, I was trying to explain the fine structure constant. I really wanted an explanation for this, because I hadn't gotten through the coherent system of units mystery yet. I hadn't burst that bubble, right? But I knew that if any explanation of reality was ever going to come to a human in the future, it was going to include a geometric answer for what this number was, like pi, right? We would have to know it, like we know circles. So I knew that there was a geometry we were missing. So I was just searching for that one. I wasn't prioritizing the rest. I was prioritizing this one over them by far. But somebody sent me an equation that was very close to this. It didn't have this part. It got right the first 7 significant digits. And that was, maybe it was 6, but still, I'd been looking for years at that point. There's plenty of people online who try to come up with crazy equations that get you close to the fine structure constant, right? There's people publish their entire publications of crazy ways, and they get you to 2 or 3 or 4 significant digits. I think I saw once that was 5, but it had like so many parameters to tweak it. I was like, yeah, that's artificial, right? This one that he sent me got right to 7. Maybe it was 6, but close to 7 right away. And this point was at the point where I was used to things being right up to 7. I could never get past 7, right? It was only up to 7 that the geometries would work, but after 7 it was always wrong. And then I realized, wait a second, we derived the Planck constants from the constants of nature, which almost all have more than 7 significant digits. So if the Planck constants are leading to those, then that must mean there's contradiction between the Planck constants after 7 significant digits. There has to be another piece. Right? They all agree after the first 7 significant digits, there has to be another piece in play. And
You're right, there has to be another piece.
yeah. Well, when I rewrote the equation, and first of all, I sent it back to him, rewrote it kind of like this, without this, and said, oh, thank you. I thanked him, for sending this to me. I hadn't seen this. This is the best one I've ever seen, and I have a real good feeling about it. I was already onto it, but he came back right away and said, oh yeah, but it's off by this much, right? And I was like, yes, he's gonna get it. He's totally gonna get it. That's the first thing I checked. Gives me an answer, oh my God, it's the closest one we've ever had. And then I just said, well, what would you have to change this equation by? That's what I had. What would you have to change this equation by to make it all the way right? I don't know. I put minus x, and it spits out the Planck mass as the answer. I'm like, what the? Okay, but now remember, at this point, I just now had a full geometric match with the number that gives us the fine structure constant. But I have an equation that in order to give us that, it gave us all 4 of these. It didn't give us just that one, it gave us all 4. I didn't want this one, this one, this one. Really, I didn't need nothing. I didn't need them for anything. So it took me a while to realize how important this equation actually was and to look closer. And the reason that it happened, or the way it happened, is I was asking a question about if I can write this one, or show you the equation in this one.
You know what is so amazing as we go over the math?
What?
There's this ongoing debate, did the universe explode into multiple different forms and eventually one, arrive where we could exist and evaluate the universe, right? But based on this math, it seems like there's only one universe that can exist.
So the minimal universe, the combinations on top, it becomes a combinatorial explosive. There's many ways you have an infinite number of Lego blocks, but only 5 kinds of Lego blocks. You can still put them together in infinite number of ways.
But you can't end up with a universe less than that.
You can't end up with a universe that's incompatible with the minimum one. All prime numbers are divisible by themselves and 1. This internal construction. This 1 is internally divided by these boundaries. It's not boundary. Okay. If we take the outside expression of the inside wrapped up hyperbolic figure 8 knot, that means its outside is hitting 1 hyperbolic figure 8 knot and 1 hyperbolic figure 8 knot on both sides externally, because remember, externally it expresses as a split cover. So it unwinds the whole volume of the hyperbolic figure 8 knot outside that way and unwinds it that way, both sides of the cone. You get the unwinding, okay? So there's 2 volumes of the hyperbolic figure 8 knot that trace out the boundary of the mass boundary, okay? What is the mass boundary though? The Planck mass boundary. So the Planck mass boundary, I could put it right here, except this hyperbolic figure 8 knot is a Mobius strip path. It has to go around twice before it gets back with the right orientation. It goes around once and now it's flipped. Now it's expressing its outside circle. It goes around another time, now it's expressing its inside circle.
Okay.
Okay?
Oh, is that why when they talk about spin, they talk about half spin and quarter spin?
Mm-hmm.
I always
half spin.
Or also when some things take 2 spins to go around.
Yeah, spinners. They take 2 spins to go around. All of them do, like electrons. It's the number 1. Well, we're getting there, but if we have this outer boundary, this just expressing 2 of the hyperbolic figure 8 knots from the inside, because there's a double cover in there and a split cover out here. But you remember each one of those takes a Mobius trip, so 2 trips each. That means we're going to have to take, I didn't need to put the parentheses, but I could just do NP, NP. I need 4 of these guys to close it. Now, I'm just going to make that look prettier and say NP to the 4th. Okay, because this is just a double of the Giesecke constant, this happens to be 4 GGI MP to the 4th. You might want to write it that way too. Same thing. Okay? This is the minimum closed 3-manifold, minimum 3-manifold possible. Our mass boundary externally is composed of 4 of them. Remember how our bottom boundary had 4 arguments? Our mass boundary has 4 expressions. Okay, well guess what? If we treat this as the same sort of construction, it has to have an inside and outside. Okay, then the part inside here ends up just being closing the hyperbolic sign. This is something I couldn't wait to talk about actually. Do you remember an equation that looks like this?
That was the outer boundaries.
This was the boundary of the space boundary.
Yeah, right there.
Inverse hyperbolic sign of, not inverse hyperbolic sign, but this one, were they both inverses? Sorry, this one's double inverse. Oops. This one, okay. So one more operational rotation, but we've closed out all of our hyperbolic splittings. What do I mean by all? This is in here, we got, I don't know if you can read it very well, I'm gonna make it bigger. Instead of being 1 over b, we have all of our derangements, all 44 of our derangements close out at this place, at this boundary. Kind of follow me so far?
Okay.
Let me write this more cleanly, it looks really ugly. 1 plus hyperbolic sign of full derangements over the break and scale symmetry, and And were they both inversed? Yes. Okay. And of course, on our terminal boundary. Okay, so we're using the same construction for all of our constants in nature with this terminal boundary part. But this part, remember, is 7 orders of magnitude smaller of a contribution to our answer than just that part. So if you only wanted an answer for what this boundary would be, what is this mass boundary when it's the minimal construction defined by the volume of the hyperbolic figure 8 knot and where all the original derangements close out? Okay. Just type in a number, or you type in alpha wolf and alpha, and it spits out a number that happens to be identical. Identical. And we know the mass of the electron really well. And it spits out the mass of the electron. Now, if that doesn't really blow your mind, then you're not paying attention.
Wait. Why?
Why? Because this arrangement of the mass boundary is the balance that the mass action is always maintaining. It's tracing out that it's coming from the hyperbolic figure not on the inside, and it's just doing the external expression of it. It's trying to undo the twisting that the twisting on the inside did. Does that answer why?
Oh, then doesn't that mean that the electron is really like the center point of the charge?
Yes. Electron becomes the definition itself of charge. It becomes the defined minimal expression of charge.
Yes.
Now, I was still very happy with my J1, but had made no sense of J2 or J3 or J4. Hadn't tried. Honestly, hadn't tried. Because I just didn't need them, right? Well, I happened to keep asking questions between all the important mass values, and the most important mass values are the electron, proton, and neutron. Both because they're the most manifest properties of the things that construct our physical world, right? But also because we know them to the most significance. So if you had an answer that explained them, much more impressive than if you have an answer that explains the mass of this one we know to 2 or 3 significant digits, right?
Yeah.
Okay, so that's amazing, that's geometric, and that's clear. This is where I first discovered that the hyperbolic figure 8 knot was involved. Kind of hard to miss now, right?
Yeah.
Okay. Okay. Now it's kind of so. And I backtracked from there. Turns out that the volume of the hyperbolic figure 8 knot has a dilogarithmic definition. We're going to really like this. So it equals, and by the way, it's internally defined or in the imaginary direction. Okay. Awesome. As 2 parts of a dilogarithmic integral. That's what this means, dilogarithm, okay?
Okay, what is a dilogarithm?
Well, you can have a logarithm that's composed of 3 parts, or 4 parts, or 5 parts, or you can have n parts. But this one's 2, so you take a logarithmic connection twice. That's a 2-part logarithmic connection.
Okay.
And if you want to put the sign in here, or the operation, that would mean of a flip. A dilogarithmic flip, and this would technically mean a negative dilogarithmic flip. Okay, but we don't want a flip. We want only a third of a flip. The other part is positive.
Oh, shit.
Okay, I think you're starting to see something.
Yes.
Sounded like you started to see something.
Well, right away I'm looking at the quarks, 1/3, 2/3.
Uh-huh. If I say, let's put Z, H, W, proton, neutron, electron. Let's do the tau, and E, okay? What are the charges of those?
Of which ones?
Which charges do you know out of all those?
Proton plus, electron minus, neutron neutral.
Good?
And then there's equivalent ones for the tau.
Yeah.
And what did you write? What were the bottom ones? ZHW.
These are all the muons.
Yeah, the muons.
Tau muon.
No, the ZHW.
Oh, Z, and the Z goes on, the Higgs, and the W goes on.
Okay.
So the Z and the W have plus and minus.
Oh, I didn't know that. I thought
They come in both.
They come in both.
H is 0. The Higgs is 0, okay? Now underneath, plus 0 minus, and then 0, 0, 0. Okay, that's half the list. Half of the particles, fundamental particles of matter, those are the charges. We're gonna call this an external arrangement. What's our total?
0.
the sum equals 0. Okay, cool. They all sum to 0 in the external arrangement. Let's do the other one, do down, and this one has the, by the way, notice the electron shows up in both patterns here. The electron likes to show up twice almost everywhere. Why?
Well, wait, the electron doesn't appear in the quarks, right?
There's an electron in this half and an electron in that half. The external half and the internal half both have an expression of the electron. Why would it show up twice?
It must have opposite
remember the
charge.
mass boundary shows up 4 times. The charge boundary shows up twice. The time boundary has an argument that splits by 4. And the space boundary splits 2. There's a 4, 2, 2, 4. Okay? Now, let's put in the numbers here. What are the values of the charges there? This is negative 1/3, negative 1/3, and negative 1/3. Negative 1, negative 1, negative 1, positive 2/3. Right? They split. The internal ones are split up into chunks of negative 1/3 and positive 2/3, or they're still the negative 1. What's the sum?
1, 0 again. Right? Okay, so the top one is 1. Right? 1/3.
1, 2, 3, negative 3.
Oh,
That's negative 4 then. And then plus 6/3, so plus 2.
2.
So negative 2. Negative 2. There is a total charge of negative 2. Before we care about the total, what about these splits? Negative 1/3, positive 2/3, what could that refer to?
Well, in the equation over there, but I'm not sure why.
Okay, remember, this is characterizing the volume complement of the hyperbolic figure 8 knot. It's composed of 2 dilogarithmic actions. One of them's negative, one of them's positive. But the actions are just actions that mean to be flipping. It just doesn't get the full flip. You get 1/3 of a flip, and you get 2/3 of a flip in the opposite direction. And remember, it's kind of the same thing. You can have positive 1/3 goes to here, or you can have negative 2/3 goes to there. Right?
Okay.
So you've divided the domain perfectly up. There's nothing left. You took the whole thing with 1/3 and 2/3. So we've split our domain internally into things that rotate into 1/3 and 2/3 actions. And here, the charge splits are exactly negative 1/3 and positive 2/3. Okay? It's a good start. We're now going to erase all this because I really need to get the masses. It's really cool to see how we got charge boundaries. The charge wasn't that complicated because that was the whole pattern. That was all the charges of every fundamental particle there is, right? Not that complicated of a pattern. It's got negative 1/3, positive 2/3, negative 1, positive 1, or 0. That's it.
So you can either go down to, you can either get 0, -1, or +1.
Yeah, exactly. That's it. So now, because of this split division of the negative 1/3 and positive 2/3, I realized this boundary has to be, well, first of all, it's so beautiful, I think it's rather obvious that it's right. I honestly do think once you get to this point, you're like, oh, seriously? It kicks out the right number? Okay, that counts as a full explanation. I'm happy with this. Once I had that, I realized, oh, well, this is a balance of that action.
I mean,
This
you
is
must
a dull
have
balance
you
of
must
that
have
action.
freaked out when this.
Wait. Then I said, well, what happens? And I looked around for a while, so this is cutting the story short. I'll tell you in longer detail later. 2/3 we care about now. It's one of our division operators for charge, right? Especially if it's positive. I found that if you take a hyperbolic split, this is the splitting coefficient, the alpha Feigenbaum constant, okay? If you put -1, it's hyperbolic now. Well, this one's square root 2. What does this construction mean? It means we're addressing a system. In fact, maybe I shouldn't put the 2/3, but I did already. Let's start without the 2/3. If this is a balanced system coming from a vortex-ish shape, then there's going to be, this is the balanced line, there's going to be 2 other ways to talk about the exact same boundary that's forming. Because this way is talking about its balance. This is exactly the line on which the balance is reached. but it's forming a boundary. And that boundary has one balance. What's the rest of it doing? Falling apart or falling together, right? Like a vortex. Both sides, when you come out the throat, you go apart. Or this way, you go apart from each other. So two ways in which you're split apart, but then eventually you come together in another orthogonal direction, right? So I want to then encode that splitting. And this is the simplest geometric way to represent a hyperbolic square splitting. Kind of nice. Kind of nice. And also, then I might want it down here. I want to say there's going to be another arrangement. Well, I'm going to go ahead and put this one in for you. I'm going to just give this one and explain kind of more on the back end. Because in the other arrangement, I want to use the other operator. So we have, think of these as a big twist and a little twist. We'll call them that from the charge boundary, okay? And the internal construction. So big twist, little twist. The big twist is in a squared arrangement, so it gets to be squared too. And this time, we're not splitting. This time, we're joining. What are we joining?
As it comes together.
Yeah, but what comes together? What geometry is coming together? A hyperbola and a circle.
Yeah,
We're joining a hyperbola and a circle, okay? How would you represent a hyperbola or a circle?
well, circle round.
So pi or 2
Oh,
pi?
I see.
Pi or 2 pi, you would think, okay?
Okay.
So we're going to have three things. One of them is pi. The other one is 3. Why 3?
3 dimensions, I guess.
Nope, close though. Remember earlier, several hours ago, we were introducing the basic equation for hyperbola and said if it's just a regular hyperbola, not a self-closed one, just a regular hyperbola, and you get, as x approaches 1, the limiting expression of that connection is 3. So hyperbola, circle, and they are dilogarithmically connected. So we're dilogarithmically joining a hyperbola and a circle. And then we need to close out and look at the symmetry here. I really love this. 1 minus 1/3, so that's baby twist, e to the 3 Euler-Mascheroni constant on the terminal boundary. And this one, 1 plus 2/3 e to the 3 gamma on the terminal boundary. Perfect inversion symmetry. Well, so far, you kind of follow or you mostly follow?
I kind of follow.
Ask me a question. What's the trickiest or stickiest part so far? It shouldn't fully make sense yet. I haven't finished, but we're...
Because I don't know how those numbered, like, I don't know where they came from.
Okay, and so we have a balanced line, and the balanced line turns out to have two other expressions, right? You can talk about it in its balanced way, or you can talk about it in the way it's maximally tearing apart, or in the way that it's coming together maximally. So we have 3 orthogonal limiting expressions of this one boundary. And if I want to characterize them, I know I've got the balance down. So it motivated me to go look for the way to characterize the way it splits. Turns out that this equals to J1, and this is squared, and the mass of the electron over the mass of the proton. I'm going to put that for the symbol. This is 1.
Mass of the
But I
electron.
had to have, when I put in the right answers there, it kicked out this number, J2 squared, as the answer. When I discovered that I needed J2 to give me the proton,
So at first you didn't even know why you needed it.
no, I had no idea that J2 was important. I hadn't looked to see that you could do all this with it. I didn't know any. I just wanted the fine structure constant. And afterwards found out that the parameter that gives us the fine structure constant comes with 3 sisters, and together they give us all of this basic geometry that we really love, right? Not to mention the fine structure constant that we couldn't explain. But now the second one and the first one are involved in converting from the electron to the proton. And the conversion is the hyperbolic connection we defined, and the hyperbolic splitting with the big twist squared, and inversely, the other split that's splitting e to 3 gamma. E to 3 gamma is like, do you already know? Have you seen this before a lot?
No.
The Euler-Mascheroni constant is the big mysterious constant, like why does it always show up, okay? But it's the limiting difference between the natural, or the harmonic series and the natural logarithm. So there's some sort of harmonic thing happening and a logarithmic thing happening. And when you take the difference between the two, that guy shows up.
Oh, interesting.
Uh-huh.
And that has some kind of pattern that, you know. But then you're saying that you can transform, did you say transform the negative charge into the positive charge, or electron to a proton?
Right here, this is a prescription, how to transform it. This is how the electron and the proton geometrically relate to each other. The electron is the balance line of the mass boundary. The proton is the way the balance line tears apart maximally. The neutron is the way it comes back together.
So what we're saying is we can convert a proton into an electron by, in a sense, moving it from one place to another.
More important,
geometric
better.
space.
We're saying that we have a balanced minimal geometric construction whose mass boundary, the dimension of mass itself, takes on the minimal balance that defines the electron's magnitude. And that same balance looked at 90 degrees. You didn't need to convert anything. You needed to look at it at 90 degrees is tearing itself apart as a proton all the time or it wouldn't exist. And it's coming together as a neutron. In the minimal possible construction, all three of them are always there. You don't need to convert, you just need to access one versus the other.
They're always there. So you mean the proton, electron, and neutron?
Yeah. This is about, this whole prescription, these all come together. This is the balance line of the mass boundary. This is how that same boundary splits, this is how that same boundary comes together. All three of those attributes are unique properties of the mass boundary. So we get three unique numbers that characterize it. Its balance, its tear apart, and its come together aspects, right?
So it's like saying where it is in the life cycle.
Okay, good. Where it is in the life cycle or where you probed it. Did you probe it along the balance? Say the balance is doing this. This is its path, doing a thing like this. Are you probing along with the balance? Then you're getting the electron. Or is it going like this and you're coming this way at 90 degrees? Then you're going to measure a neutron.
Okay, right, because you're going straight across and you're not affected by the wave.
Yeah, you're not either with the balance, exactly against the balance, how it tears apart, or how that tear apart is coming together. Remember how before I said that the mass boundary is the outside expression of the space boundary? Remember how this is the inside equation for the space boundary? And here's the expression for the outside of it. Here, defining the mass boundary.
Oh, shit.
Yeah. Really, really, really beautiful. But also notice we have plus 2/3, I could say minus. So it's perfectly minus 1/3, minus 1/3, plus 2/3, plus 2/3. The right parameters that are dividing everything up. And the only other ones in here are the most important constructive parameters in all of geometry or math, the one that defines the splitting coefficient of reality, right? Bifurcation parameter called the alpha-Feigenbaum constant. And the joining one is joining a hyperbola and a circle dialogarithmically, which we already knew. We already knew a dialogarithm was involved.
So basically, negating one of those would turn. It's where we get our antiparticles from. There's one thing that's hiding in there.
What?
Where is the neutrino?
Oh. You're gonna love this, man.
You found the neutrino?
You're gonna love this. This is so exciting. Okay, that pattern about.
By the way, the neutrino is like my new favorite particle.
Is it?
You know, it's like picking your favorite beetle, I guess. But like the uses of the neutrino, like, could be incredible.
Yeah, no kidding. If we get a way to use a neutrino, that's a completely different level of technology. And the only way we're ever going to do that is by understanding how they're all connected. This is the only hope for that.
Right, the only hope. Okay. I forgot I was even going to go into this. As soon as you asked that question, I was like, oh, we haven't done that yet? Okay, we couldn't have because this, I want you to really kind of nail this in. This is a very important pattern here. The base description of our entire mass boundary. Okay? 3 different ways to describe it, all geometric, all interconnected with the same properties, but they spit out only the electron, proton, and neutron. But as you pointed out, but what about, there's more. I mean, that's not the whole story.
right? There's more than the proton, neutron, electron. Yeah, of course the other ones are less important. What do I mean by that?
I guess they average out into becoming protons, neutrons, and electrons.
They're less obviously playing a role in the construction of reality, right? We notice them only by
we don't
looking a lot
interact with them.
harder. Yeah.
Right, we don't interact with them at all.
That's what I mean. So also maybe they're smaller, weaker, that kind of stuff, but they're still there, and since we've measured them, we need to explain why. All right. Do you think there's any chance we can go from this to an explanation that also explains all the other particles?
Actually, let me guess.
Okay.
We do know, take for example the proton.
I'm going to rewrite that one first. Go ahead, keep going.
Because the proton is made up of quarks, and some have 1/3 and 2/3, right?
Okay.
Let's see. So this has to do. So one quark, there's a formula to represent one quark that, let's say, is 1/3, and a separate formula for the. Oh, you're writing it right there. 2/3.
All right.
Such that the 3 quarks equal the sum of some charge and, I guess, mass of the proton.
Say it again.
Such that the sum total of the charges and masses of the quarks would equal the mass of the proton or neutron in question.
Okay, so you're thinking it's a composite way. It goes in.
Right.
And if you get all those, then it makes the one, and get all those, it makes another.
Right.
Nope, it's a little different. This same one mass boundary that we've described so far, we've only got one mass boundary with 3 attributes.
Okay.
Like it's balanced, it's tearing apart, and it's coming together attributes. But that same mass boundary can be tiled in 17 unique ways because all 2-dimensional closed structures can be tiled in 17 possible ways. And those other possible tilings define the other possible elementary masses.
17 possible combinations.
Tilings. So 17, so you have a shape that's closed, a 2-dimensional shape that closes over time. Once you got that whole shape, you can put down a tile of a certain shape and cover the whole thing and not have any gaps. Turns out there's exactly 17 shapes by which you could tile the structure, including the electron, proton, neutron has one of those 17, that cover the same boundary. So we're going to be talking about the one mass boundary every single time, and we're going to have 17 expressions of the mass boundary. Okay? And how do we get to those? Well, we start with this one.
I'm also latched on to the fact that you said 2-dimensional. 17 2-dimensional.
Yes, it's a 2-dimensional boundary because it's a closed surface. So just like this is a 2-dimensional surface right now, but it's not a manifold because it's not closed. Meaning if an ant was walking along, it could fall off.
Okay.
But if I go like this, and glue these edges together so that they're gone, there's no edge on that part. Now it can't fall off that way, but it can fall off this way. And so if I twist those together and glue those, now it's a 2-dimensional boundary that's closed and the ant can't walk off it.
Oh, I see. So it's where you're talking about a closed 2-dimensional plane. Surface. I'm thinking of it as 3D because
it's embedded in 3D.
It's embedded in 3D.
It's a 2-dimensional surface embedded in 3D, but you can tile it exactly 17 ways. And this is a general rule for all 2-dimensional surfaces, nothing to do with me. Okay, when I discovered that was, I'm like, what? It's always 17? Yes, there's exactly 17 plane symmetries.
I just realized, I never realized before, there is a difference between a closed 2-dimensional surface and 3D.
Okay.
Like you said,
of course.
It can exist in 3D.
Exactly.
It doesn't, in fact, it does exist in 3D, but it's not of itself 3D. It's a closed 2D.
Exactly. In fact, it might be generating or responsible for the fact that there is 3D, but it itself is 2D.
That's a really amazing insight right there.
It is. That's like one of the main insights of manifolds to begin with. It's like a mind-blowing, what's a manifold? It's a type of geometry, a type that an ant could be on but never fall off. Right? There's no edge.
And you're saying there's 17 different shapes it could be in.
No matter what 2-dimensional surface you have, even if it's just an infinite plane, there are 17 possible tilings you could pick, shapes of tiles, in which you could put it on the plane, give me another one of those, another one, and you could fill the entire plane with no gaps. 17 intrinsic types of geometries in which you could tile it. That's a universal thing. All right, just because it's 2 dimensions. Now look here, I think, well, actually I want to see what you say when we do this. This is a 1/3 squared. This is the mass of the Higgs, the Z and the W. The mass of the down, up, and electron again. Shows it twice, everywhere. And again, I'm repeating the neutron, proton, electron one from here. So I'm taking just one of our three, the way it's fallen together, and we're extending it, okay? Kind of nice so far, huh? Well, this time I need to erase, give me some room here. That's 1 plus. Here I'm going to put 2 to the 0. Still just 1, right?
Okay.
Why? Why do I want to modify that? Because this one happens to be 2 to the minus 1, and this one's 2 to the plus 1. So this is the modification. Other than that 2, because there's 2 of them externally. They're all the same, we're extending, except for we're letting this one be 1/2 and that one be 2 compared to the others. A split and double on both sides, okay? And then I had to check the Wolfram alpha to see what these answers were. But this one's, sorry, I wrote that wrong. This is a 1 cubed squared. And here's you got the Dottie constant. This is the universal trivial cosine connection. That one, that, and this one. 2 squared. 1 cubed again. This time it's the Gauss constant. I don't think you know what those are yet, but we'll get into them when we get to the London state constant and so on. But it's a fundamental geometric operator, okay? Still, these are less important than the rest. You can kind of see just from this part. It's less important significant digit-wise. They're way out 7. That's where they start. Here, the only thing that changed was we take the 2 to the 0 and we give it its -1 and +1 phase. Okay?
Okay.
Just change that. And now all of a sudden, instead of talking about the neutron, proton, electron arrangement, we're talking about the Higgs Z or W arrangement, or the D, U, E arrangement.
So they're different arrangements of the same thing.
Yeah. Different arrangements of the same thing. You got just a different expression here, but now you said we've doubled this one, we've halved that, and we've doubled this one without changing this. We got those different arrangements, and we get different expressions that characterize, that spit out the right number for the mass of the down and the mass of the up, the mass of the Higgs, the Z, and the W. From this, notice we just took the same thing and extended it, okay? That's externally. Externally, we have those 3 phases. Internally, we'll extend the same thing.
Hold on a sec. Right now, you said there's 17, but we see 9. Right?
Yeah. That's exactly where we're going. So this is external phases. -1, 0, +1.
Okay.
Now I'm going to do internal folds. This is to match the opposite of what's happening there. And this time we get that's a 2. It's an interesting upset right there. Just like the interesting upset here.
Okay.
I like that the upsets are only 2s.
Makes you wonder why. But
Well, I kind of know why, but I just wanted you to pay attention to it. It's your first time seeing it, I think, right?
yeah.
So hopefully you're absorbing that the patterns here, they have a lot in common, right? It's easy to see what I mean. We extended the first one to all of these, right? Do you follow what I mean by that?
Yeah, because these folds represent those things.
Yeah. All right, but now you need the external half, or you need this part, right? For each one. Watch this. That one has 0 terminal part. It's right all the way to all 14 already. And this one, on both sides, it's 0. And this time it's It's
So
got
what are we saying?
Yeah, good. How do we read this? So in this one, first ignore these. We notice what's happening is that we repeat the same thing over and over that we started with. The only difference is now we times it by 4 or 4 squared, or right, it goes up in power each time. So we're crossing and getting a whole other copy and copy and copy, and it becomes more and more and more. So this is internally folding in opposition to this phase spreading. What do you think of it?
So
You see the patterns, right?
Yeah, but we're defining, this is defining, oh, right, the internal folds, right, it is.
By the way, this part right here, I'm totally happy to have changed if we come up with a clearer, shorter math thing that represents it. It's just the one that pops out that I could find. So if we do find something better, I don't know how to interpret fully that. I partially do. I know it's parameters in pieces. Same thing with this one, okay? That one, I love to death. So far, out of everything I've shown you, these two are pieces that we could change if we find a better solution, but that's what the things, I've just followed what Wolfram Alpha shows me is the right answer. So we'll either make some more sense of that or change that in the future, but yeah.
Or maybe as we're writing functions,
Yeah, exactly.
we'll come up with it.
Yeah, or make sense of it, yeah. Fully, but I still don't know how to put that to words too much. But the rest of this really makes a lot of sense to me. And what I really want you to notice is, we started out with the most important one. The one that we know, by the way, to the most significant digits are up here. So explaining that's the hardest. And that pattern extended, we just took one of its parts and were able to extend it in a way that nailed every single mass particle. And now we're going to take the other one, the middle one, and do the same thing and get all 17 mass particles with the same answers.
But are there 17 mass particles? We went through 9.
No, right here. There's the rest.
Well, what do we call them in?
Charm, strange, the muon, the top, the tau, the bottom quark, the muon, the 3 neutrinos.
You're right.
Yeah, those are different than those.
Yes,
And
you're
the
right.
only difference is external phase versus internal fold.
That's where I've been wrong. I always thought of the proton as made up of those things, like building blocks.
So did I. That's what
But
we were
they're
taught.
actually equal partners.
They're constructively all, I mean, some of them are bigger than others. They're not equal in full all the senses, but
Right.
they're all parts of one system. And all of these, by the way, are just, this is a different layer in which you describe the same connection, right?
But then why would they say that a proton has like 2 ups and 1 down or something like that?
It does. Look close. There is a neutron minus a proton on this level over an electron. And we went down here, and the neutron turned into a down, and the proton turned into an up. Keep staring, it's going to pop in some light. The constructive connection of everything they're saying is still in here. But I think maybe the way they worded it together kind of misled us a bit. Because what we're really talking about is just one balance that happens to be tearing apart one way and falling together another way. And if you only use the way it falls together to characterize all the possible expressions allowed, you get them all. And now we're going to take another 5-10 minutes to use the other one to show you also get them all the same all.
But now here's a question.
Okay?
How can I formulate this? The proton is made up of, I think, 2 ups and 1 down, right? Or 2 downs, I think.
Yeah, I can't remember.
Whichever way it goes. Are we
2
saying
ups.
that?
Let's go with 2 ups because it's on that side.
Okay.
Okay, so you got this? What I'm trying to say here?
Yes.
Does it feel mostly make sense? I know it didn't make sense of that part, but.
Yeah, I think it mostly makes sense.
Okay.
Like, I think I need like a day or 2 to sleep on and internalize it, but I think
Okay.
I kind of get.
In general, all you had to notice is that we extended just this one line, which came from the bottom over there, into a pattern that captured all of the mass particles. On this one board, we have all 17 mass particles, okay? Now, let's use the other one, just because this is really amazing, and it helps give you confidence in the story so far. So if what we're describing with the mass boundary is this specific balance, and so far, we really care about its major expression of balance. We also really care about the way it comes together, because that way it comes together extends into accurate expressions of all 17 mass particles. We also care about the way it falls apart and get the same particles. Why? Well, because it has to be the same system. They're talking about each other. You can see from the two compared to each other that they're inversions of each other. You can kind of tell right away. So let's take the middle one now. Mass of the electron, mass of the proton. 2/1 squared equals big twist squared alpha phi gamma minus 1 squared. So
What are we about to describe?
we're about to do the same thing we just did with this one. We're going to extend this pattern into a pattern that captures all of the 17 particles again from just these. That's really bad. Does that make sense or not make sense?
What we're saying, with one equation, we can define all the particles.
Yeah, I'm saying that we extended just this one into capturing all the particles, and at the same time, we can extend just that one to get all the particles. And they both tell us the same answers.
Because we got to it from two different ways.
Yeah, two different ways, by extending, generalizing the two different patterns. Yeah. All right, this one and that one. All right, let's see if you can get the pattern that happens here. You recognize the symbols? Which particles we're talking about?
The tau, you took out the T's?
Yeah, top, char, this one's the charm, this one's the,
Charm. Yeah, I
this
don't
one's the top. So in each case, it's the same three on top and on bottom. Okay?
Okay.
So this is bottom, bottom, charm, charm, top, top. But there's 3 of them. We started out with 2, we extend to 3 of them. Wait, how could this be an extension of that? Think about that for a second, and let me show you what it comes to. Okay, and then there's the electron, muon, tau. This is the universal parabolic constant. Very nice, also geometric. Okay, so that's our full splitting map, and then we got to do the other half, the split balance on the inside. So far, the pattern on this half is pretty easy to see. 3, 2, 1, 2, 2, 0. Why? You have to have, apparently this arrangement must be in a square arrangement or you don't get it. All right, the other half, the Higgs plus the Z plus, notice that these are constructively different ways of putting these things together, right, than we did before. If you can still remember, I erased it already, but. And it's the same.
Yeah, but before we were using 2, now we're using 3.
Yeah. This time it equals 2/3 to the negative 1/2 alpha phi gamma minus 1 to the negative e to the 2 gamma. That's really interesting, of course, but let's keep going. 1 squared and 2 n v times VFE to the 1/3 negative 1/2. There's a lot in that that's detailed, but I really care most about the left halves right now. If we notice the patterns, at least the left halves. Okay?
This is kind of the side. Does this mean that the strong force doesn't really exist because it's only geometry? There is no force.
It is still a real thing. Yeah, there is no force in that sense. Yes, kind of. But it also is the most real thing there is. It's the only thing that actually exists because the rules of persistence what determines what is, right? So
Actually, in a
it's
sense,
not
the
what you
rule-
thought it was, but
Right.
it is. Yeah.
The rules of persistence is the strong force.
Yes. Yes. Good. I love that. All right. Now we do the up, and we do the strange, and we do the down. Those are good ones to get. Same exact pattern. Square root of up plus the square root of strange plus the square root of down. Squared. So that's the sum. The sum over the square of square roots. But if you think of the square root as the element, the square root of the mass as the element, then it's the square of the sum, or sorry, these are squares then, so the sum of squares over the square of the sum. Follow me? At least algebraically, if you let yourself think of this as the x as the operator, the square root of the mass.
Oh,
as the thing. Then this is the
wouldn't that
sum
equal
of masses squared underneath the squared sum. Right? Squared sum over the squared sum over the sum squared. It's hard to say. What were you going to ask?
I just realized the strong force is considered one of the fundamental forces in nature, but it's not a force. It's kind of like the so-called force of gravity, which is not a force.
Okay. All of them, yes. All of them. In the same way that gravity is a geometry, it's still a force in the sense if you want to put yourself in a frame that ignores all the geometry that's going on, then there's a magical thing happening as a force, right? It still would be there in that sense. But it requires you to frame yourself Euclidean way for that thing to be a force, the action to be a force, yeah.
Right. Actually, that's interesting.
Look at this one, by the way. It's one of my favorite equations in here. Remember how the Euler-Mascheroni constant was a fundamental mystery in math alone? Well, here, 2/3 goes to 0, and the alpha phi bar minus 1 goes to 0, and the external opponent goes to 0. So technically, I could just say, this one is just equal to the Euler-Mascheroni constant. Okay?
Holy shit.
Okay, and then the bottom one, I had to completely make up and guess. So let me show you how I make up and guess stuff. This is the one that I don't know the answer. But to complete the pattern, why don't I know it? Because my method allows me to use things we have measurements for to check. It gives me nothing for things that we don't have measurements for. Except we can guess from our patterns. So if we're only missing one thing, I'm guessing this is 2/3 to -1/2, just like above. And why do I guess? Because all the ones in between canceled out. And this I'm going to put at 2NB. VFE, this time with the positive 2/3, -1/2. But I did make it up. That did not come from data. Okay, so you can kind of see this might be entirely wrong. By the way, that was true for the last one. On the first one I filled out for you, when it came to the neutrinos, I guessed the pattern.
But is this what you think the neutrino is right here?
Yeah. This is what I think the mass expression of a neutrino is bound by, and the other one. So those are the characteristics of the neutrino. And why? Because algebraically, this balances out. First of all, this is splitting around, and this is a division parameter to begin with. So everything is a split and flip. This e to the 2 gamma and this e to the pi I. E to the pi I is -1. I can just replace this with a -1, right? But -1 means flip. This is a flip, and this is a split. Flip, split, and they have to be balanced, so I put them at the same inversion.
From the geometry, I can see why a photon would be a particle or a wave.
Keep going.
Because if there's any wave, so to speak, any disturbance whatsoever would be a wave in the balance of the figure 8 knot.
Yep.
Right?
If it's going to continue to persist.
If it's going to continue to persist. Like most times the waves, sometimes waves might collapse a piece of reality, but a new piece appears.
Yeah.
So waves can either travel through this without disturbing it, maybe distorting it, which probably happens most time. It distorts it. And
which internally isn't even detectable.
Internally, it wouldn't be detectable.
Yeah.
You're
Because
right.
all of your comparisons are still the things you're referencing from.
Right. So when a wave is traveling through you, you won't know it.
Yeah.
Okay, so then the wave travels through, but at any point in the geometry of that hyperbolic figure 8 knot, wherever the wave happens to be, there's a disturbance that looks like a point, kind of like that would have a midpoint.
Okay.
And if it has a midpoint, it would begin to look like a particle.
Yeah, or if it has any partitioning happening, meaning it splits. If there's a splitting, there's going to be a wall invented, right?
Right. And
so that we get particle properties all of a sudden that come into existence. Yeah.
And as a matter of fact, as it's traveling, it actually is a particle at that point where the wave is, where it's going.
Yeah, the particle wave distinction becomes like an inherent part of this system, right? It's every particle has wave characteristics. It exists as a pushed together set of boundaries from waves.
Okay, but now, when we go back to the other formulas, we came up with, you know, proton and electron can collapse or combine into a neutron. But it didn't account for the mass of the neutrino. So where did that extra mass come from?
You mean the neutrinos?
Yeah, this. How does that collapse with a proton and electron?
Okay, well, let's back up. This one comes from the list in the middle. So this is the list. We have a different equation for the neutrinos also, right? For
Right.
the bottom list. Right now it's just the middle list. When we get to the neutrinos, of course, we made that up. But what it's supposed to be representing is how these structures go in hierarchies. This, if you go inside, there's a hierarchical arrangement where you can have 3 big twists, 2 big twists, 1 big twist. It's the twisting hierarchy here. And in each case, you're going to keep both splits and both splits, or at the bottom level, there's no splits involved. You have to have an even amount of splits. Okay? This cancels this whole one out, which means this thing's very, very close to just being equal to 2/3, right? For the first 7 significant digits. It's just 2/3, that's cool. And that extension, then, if we extend the other way, so instead of doing number of twists, now we're doing the other 90-degree extension, and now we're doing splitting these twists themselves. When we take the negative square root of the twists, right, on that side, and here, since we're square rooting, we're not doing to the 1 or 2 power or 0 power. Now, the action of the split, the hyperbolic split itself, gets transformed under operation of 2 splittings, or 1 flip. Which side do you want to look at? The splitting side or the flip side? That's it, but they're expressing the opposites of the same thing. And what thing are they what's the center point of this action of split and flip? That guy. 3 things constructively make this middle balance. And then off the sides, you get the 3 expression, the other side, the 3, the whole balance, these 3 come together as one whole balance. These 3 come together as one whole balance, but they're hierarchy expressions of the balance. Do you remember when they do this? Let's see, 1 over 0 factorial plus 1 over 1 factorial. Have you seen this sequence? And so on?
That looks familiar from somewhere. It may be something you once told me, or like, I don't know where I saw that before. What is that?
Equals the hyperbolic base of logarithms. It's a number we really care about in our construction. But why? A few reasons. Because it's the hyperbolic base, and our structure is hyperbolic. Kind of the biggest reason. Okay? But what does that even mean? It's important to realize that it means something related to this. E is constructively equal to the infinite sum of inverse factorizations. The whole sequence to infinity. It's equal to it. Beautiful. What I'm trying to point out, it's constructively equal to it. Factorizations, the sequence of factorizations out to infinity, are encoded by the base of hyperbolic logarithms. And even weirder, or more beautifully to add, I don't know, all of it's kind of weird in the sense that like, wow, it's so amazing. You have to kind of absorb it first, but this one is 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1
I wouldn't have expected
factorial.
that.
That's a beautiful symmetry. You got its inverse operation by changing the sequence of the numbers. Just the sign of the sequence, the same exact sequence of numbers, but only alternating the signs creates your inverse. Beautiful.
That is so weird.
So we really care about E in this context where we care about things that are decomposed, that are factored, okay? Which we really care about because we gave a derangement theory at the bottom of time. Time was based on derangements. The lowest level substrate of our structure is derangement. It's written in the language of derangements, right? This is written in the language of derangements, E itself. But look, if we take the Planck union equal to the sum of the partitions of the 5 actions divided by the product of the 5 rotations. What are the 5 partitions? 44 for time, 35 for space, 18 for charge, 8 for mass, and 32 for temperature. Okay? Add all those up, that's our total partitions. Remember what I mean by the partitions? 44 on the time boundary?
Right.
Okay. The product of those is just the first time rotation, the space rotation, the charge rotation, the mass rotation, and the temperature rotation. And that equals, wait, we're not done though, because all of our constructions have two balances.
No, that.
One, is it minus? I think it's plus. Could be minus here. The gamma function on the closed boundary. Now I have to put an argument in the gamma function, we'll get that later and so on. But my point is, this constructive arrangement between our partitions and rotations of the whole structure at once gives us the return of, first and foremost, the hyperbolic base, and inversely on the other boundary, on the opposite side, connecting the hyperbolic base, is the gamma function which defines the hyperbolic partitions. The gamma function defines hyperbolic partitioning. So we have the hyperbolic base for how things hyperbolically connect, and the hyperbolic partitioning for how they hyperbolically split, as one balance defined by these operators. Beautiful. Really beautiful.
That looks like that isn't even possible, that would.
I know. This, because of this, by the way, this is so ironclad in where we're going to go next. It's a very, very secure thing. But the gamma function itself ends up being something, because it's, look, when we combine all of these operators, it gives us this, and inversely this. This is the connections. This is like the way you would think to describe it in the terms of the hyperbolic figure eight knot, normal geometry balances, and so on. But you can describe balances inversely as things that are falling apart too. And this guy characterizes that, but if I just use the gamma function, I can characterize all 5 rotations of the time, space, charge, mass, and temperature boundaries just in terms of the gamma function in one equation at once. Structurally, when I'm characterizing its internal structure. So in short, the gamma function itself ends up being something that's intrinsically 100% this same system. It's just talking about it from the way it falls apart instead of the way it falls together. If it's characterized, it nails the same exact 5 rotations as these.
So what it really keeps coming back to the fact that physics is just solidified geometry.
Yep, that's a good way to say it. Physics is solidified geometry, and because there's a minimal way you can arrange things geometrically, there are minimal partitions of all the kinds of balance actions that are allowed under that persistent form, right? It's very simple compared to what we were guessing before, and it's a precise answer, because we're saying there's very specific geometric boundaries and interactions and relationships, and all definable. They're not vague things that you can't explore. They're all things you should explore. Yeah, anyway,
Wow.
Okay, done.